Ladies and gentlemen, welcome to The Ancient Data Scientist. Today's question is, why do we age? And I think it's a good question. What purpose does it serve? Isn't this something evolution should have gotten rid of years and eons ago? Because, well, if you get old, if you get frail and weak and die, we can't have children, we can't pass our genes into the gene pool as much as we could if we were healthier for younger. So, has an evolution a very strong incentive to select against aging? What's wrong with this argument? Today, we're going to take a look at the brutal mass of survival and at the end of the video, understand exactly why we age and how this fits into this theory of evolution and what this does tell us about the process of aging. Let's dive right in. I promised you some grim mass of survival, I think it was said. I think this graph delivers. This graph shows you your mortality rate by age. So what that means is the y-axis shows the chance that you don't make your next birthday. And as you can see, it increases dramatically with age. And if you get older than 80, it's actually in the single digits. It will even get into the double digits in the 90s, although the data isn't shown here. And this is really what's at the heart of aging. It's a rapidly increasing risk of dying in a given year. If we wouldn't age, this would be a flat line, ideally. In case you're wondering where I got this data, I got this from the CDC, which is the Center for Disease Control and Prevention. It's American data from the years 1999 until 2020. So it's definitely Western world data. And if you use this wonderful 90s interface here, you will get a text file like this one, and then you can write let GPT write some nice code to actually read this data. As you can see here, I did not read the all-cause mortality file, but the internal mortality and external mortality files. And this is the key differentiation we need to make for this data to be helpful in our quest to understand the evolutionary cause of aging. Internal mortality refers to things like heart attack, stroke, cancer, and external is getting run over by a car, falling down a set of stairs, getting shot, or getting eaten by a lion, whatever. So at the moment we just get internal and external mortality and we sum them up to all-cause mortality, and I showed you the plot for all-cause mortality. But let me take this out and let me show you the separate plots. And here they are. And as you can see, okay, internal mortality absolutely dominates the market. External mortality is so low as to basically be negligible. And that's very interesting because that doesn't help us at all in understanding the origin of aging in the context of evolution, because this looks like, okay, evolution should have a really strong incentive to reduce this internal mortality so we can still have babies when we are 80, right? Yeah, but that's not how it looked like for basically all of human history. For basically all of human history, external mortality was much, much, much higher because you were living in the wild. You didn't have shelter. If you broke your arm, nobody could set it. You didn't have antibiotics, etc., etc. So what I want to do today is actually do some very easy simulated experiments with gene injections and see how our life expectancy changes based on that. So first of all, to get a grip on that, we need some life expectancy, right? Until now, I've just shown you the plot. So let's get some actual life expectancy in here. If I run this, we get to a very healthy life expectancy of 75 years. In case you are confused why that is so low, it's because our data only goes to 84, so we act as if everybody dies at 85. Now the interesting part comes. At the moment, this is all for modern data in the last 20-25 years. However, for our most, if not all of our evolutionary history, external mortality was much, much higher. So I'm going to do that now artificially with a very simple model. I'm going to set the external mortality to a 1 in 50 chance of not seeing your next birthday at any given age. So if I rerun the code now, I get a very different graph, a graph where external and internal mortality seem to have about similar contributions, just from what we can see with the eye. And we get a very, very sharp drop in life expectancy to 38 years. And so far, that's not really surprising. If we get eaten by lions and wolves and whatever all day, of course we're not gonna live that long. The really interesting part now comes when we start to introducing gene mutations. And I'm gonna do this here in a very simplified model, but one I think that catches exactly what we want to know. I'm just gonna look at a gene in terms of how it changes our internal and external mortality. So internal mortality could be effects like less cancer, less heart disease, less stroke. And external mortality could be that we are faster, so we can outrun the line, we have tougher bones, so they don't break as much, our immune system is better, etc., etc. So if we start with this process with gene A, it's a fantastic gene. We just have our internal mortality cut in half, no detriment to anything else. If we rerun the code, we get this graph. Again, a lot of pronunciation on external mortality, much higher this time. But we only get a very slight change in life expectancy of a single year, jump from 38 to 39 years. And this is not much for a gene that does something as amazing as cut your internal chance of death in two. However, if you think about it a bit, that makes perfect sense, because your internal mortality only starts to play a role really late in life, and most times you won't make it there because you will have died of something else entirely before then. However, if I introduce gene B, which is the same as gene A, but for external mortality, the story looks totally different. I get a dramatic jump to 52 years of age in life expectancy, so 14 years more. Okay, this is interesting. What does it tell us? That tells us that the evolutionary pressure to promote gene A in the gene pool is much, much, much less, more than an order of magnitude actually, than gene B. With gene B, I live longer, healthier, I have more reproductive years, I have more children, etc., etc. Gene A is still good and evolution will select for it, but not nearly as strongly as for gene B. And if this is the whole story, you might think that, okay, it looks like aging is a phenomenon of neglect. Gene A just isn't getting promoted enough. Maybe evolution just hasn't reached its optimum yet, and this is why we age. However, that's not the whole story. The real kicker comes if I introduce gene C. And gene C, it's what's called a pleiotropic gene. And this is just a very complicated name for a gene that does two things at once, which is a very realistic thing that happens all the time. And you can see it here, gene C, it improves our external mortality to the detriment of the internal mortality. So it's basically the steroid gene, right? You take steroids, you get bigger and stronger, but you get a heart attack earlier. This is basically gene C. And if I run the simulation, I don't know if you can call it simulation, it's fairly simple after all, we can see that we get a beautiful life expectancy of 49 years, so 11 more years compared to our baseline of 38 years. And this very clearly shows us that evolution will take gene C anytime. And therein lies the heart of the evolutionary reason for aging. Evolution actually tries to maximize our life expectancy, but our life expectancy is not just a function of how we are doing internally, how much heart disease we get, but also on how well we can survive in the external environment. And evolution will pick genes that maximize our life expectancy in the external environment. And for almost all of the time humans have lived, that has been a harsh environment. So we have lots of gene Cs in our gene pool. This is called the antagonistic pleiotropic theory of aging, just in case you want to look that up further. I hate the name, it's very complicated, but it actually makes sense. So, what's the key takeaway of all of this? For me, it's definitely that there must be more than one cause of aging, because there have been many steroid genes along our evolutionary history, and of course from time to time evolution would pick one. And this very closely relates to what scientists call the hallmarks of aging, which is a very rough list scientists have come up with to list off all the different root causes of aging. And it's very rough still because it's ongoing science. But if someone is telling you that they've identified the one underlying cause of aging, you should be very suspicious indeed, because it doesn't really square with how how aging evolved in the context of evolution. Okay, I hope you have had a great time. See you in the next video. Bye.